The second most important building block of deep neural nets is convolutional neural network, or CNN. In this discussion, we will take a look at convolution and its associated operations. CNN is our closest model on how our vision works. It uses an operation called convolution from the Latin words con and volvere. Mathematically, we express the convolution operation with the star notation. In this example, our input feature is x. Using a kernel k, we perform a convolution operation. The output feature is y. In NLP, we train our models to learn the optimal weights and biases, which we collectively call parameters. In CNN, we train our models to learn the optimal kernel weights and bias, which we also call parameters. Let us take a look at one convolution operation. In this example, we have 3 input feature maps. We would like to perform a convolution that produces 4 feature maps. In this case, we use 4 filters. The first filter produces the first feature map in yellow. The orange filter produces the orange feature map. The same for the green and blue filters. From here, we can see that the convolution needs kernel size, k by k, the number of filters f, and the depth of each filter, d. These are the terms in the gray boxes. For each filter, there is also an optional bias term. Practically, we can treat each convolutional layer as a small function in our function approximator discussion earlier. Similar to MLP, if we connect in cascade multiple layers to form a CNN model, we can use it to approximate a function. Like in MLP, the deeper is the network, the more representation it learns. The more complex is the function it can approximate. Let us take a look at why CNN models are effective and efficient. First, kernel is very small compared to the input feature. For example, a kernel size of 3 by 3 compared to the ImageNet 224 by 224 by 3 in ImageNet classification. Second, parameters of the same filter is shared during convolution operation. Lastly, the increasing receptive field size as depth increases enables the output layer to base its decision on different feature scales. To understand receptive field, here is a side view of 3 layers of CNN. For simplicity, assume that each layer has 1 feature map. All feature maps are of equal size. Assume a 3 by 3 kernel is used. At the topmost layer, we can visualize all orange circles below are directly affecting the topmost orange circle. We can see that the receptive field size increases as we go down the shallow layers. CNN models have certain unique properties that make them effective and efficient on vision tasks. First, CNNs are scale invariant, meaning CNNs work regardless of the target object size. In this example, we can see that the size of lemon does not matter. It will still be detected. Scale invariance is due to the max pooling, which enables the CNN to utilize big receptive fields. CNNs are also translation equivariant, meaning if we translate the target object within the image, CNN models can still recognize it. Translation equivariance is due to the kernel, which is shared as it is convolved with the whole feature map. In other words, the same kernel is shared by the entire feature. However, CNNs are not rotation invariant. For example, if the CNN model can see the boat on its regular orientation, it will not be detected when the image is rotated. To make the CNN operate on rotated images, the training data must use random rotation transform. Similar to MLPs, CNNs use additional operators and configurations to achieve better performance. We also use activation with the same purpose as in MLP. However, there are certain operations that are mainly applicable on convolution operations, such as padding, pooling, and strides. Let us visualize each of these operators. First is convolution. In this slide, we have a 3x3 kernel moving one step at a time during the convolution process. Since the convolution is hard to visualize with an actual image, let us use a smaller image. Let us use a simpler setup to understand convolution process. We use a 4x4 input feature X and a 2x2 kernel K. The yellow highlight shows one step of the convolution process. The output feature is Y, which is 3x3. The first element of Y, which is Y11, is computed as such. Y11 is equal to 8W plus BX plus EY plus FZ. Then we slide by one element to the right to compute the second element, which is Y12. One step to the right to compute the third element. At this point, we have reached the end. The kernel restarts at the leftmost position again, but one element down. Then we compute the fourth element, the fifth, the sixth, the seventh, the eighth, and the last element that completes the convolution process. After convolution, we apply an activation function. In this slide, we show how ReLU is applied to each feature point. Downsampling is an important operation in CNNs. It is usually applied after the convolution and activation function. A popular and simple downsampling operator is max pool. In this slide, we can see how four elements are merged into one. P11 is simply the maximum among the four highlighted elements. Why is downsampling or max pooling important? The answer is to increase the receptive field size. Let us revisit the receptive field illustration before. For simplicity, we use two layers only. In this case, we can see that the top feature point is dependent on the lower three feature points. The receptive field size is 3. Suppose we use max pooling. Instead of having 8 feature points, the top layer now has 4 points. Each point is the max of every 2 points. In this case, we can now see that every top feature point is influenced by at most 4 lower feature points. The receptive field size has now increased to 4. Using a 4x4 feature, in this slide, we demonstrate max pooling with the kernel size of 2x2. Y11 is simply the max of A, B, E, and F. The rest is computed in the same manner. The same downsampling effect can be achieved by convolving with the 2x2 kernel. In this slide, we increase the stride from the default 1 to 2. Unlike max pooling, This operation effectively combines both convolution and max pooling, resulting to a much faster operation. Padding is another operation that is useful in CNNs. Recall that without padding, the convolution operation results to a smaller feature map. In our earlier example, we saw that after applying a 2x2 kernel convolution on a 4x4 feature map, the result is a 3x3 feature map. This is because we cannot go past beyond the border of the input feature map in order to keep the feature map size. To solve this problem, we use padding. We pad the feature map by zeros so the kernel can go past beyond the edge of the feature map. In this example, a 5x5 feature map is padded with zeros so that the resulting feature map size is still 5x5 after the 3x3 convolution. Note that the number of feature maps may also increase after convolution. The target number of feature maps is controlled by the number of filters. Earlier, we saw that a filter is a group of kernels with the same depth as the input feature map. In this slide, we use two filters to generate two output feature maps. In the event that we have multiple input feature maps, the output feature map is simply the sum of all kernel convolutions per filter. A big kernel has a big receptive field. However, a big kernel is computationally more expensive. Dilated convolution tries to solve this problem by using a dilated kernel, a kernel with holes but with a bigger size. The result is a bigger receptive field that is not computationally expensive. In this slide, we show the comparison between dilated convolution and a regular convolution. The resulting feature map is smaller for dilated rate greater than 1. If we want to keep the size, we must use padding. Earlier, we saw the use of downsampling. The reverse of downsampling is upsampling. It is useful in dense prediction, for example, in predicting segmentation masks. In this example, we use a simple repetition to achieve upsampling. Usually, upsampling and convolution are combined together. This operation is known as transpose convolution. This operator is useful in generating dense prediction such as object segmentation masks, as shown on this slide. Similar to MLPs, deep CNNs usually have better performance, but they are harder to train. Issues like vanishing or exploding gradients are common, resulting to unstable training. There are techniques to overcome these problems. In vanishing gradients, the gradients become near zero as they are propagated down to the shallow layers. In exploding gradients, the scenario is the reverse. The gradients explode as they reach the shallow layers. ResNet was able to solve the vanishing gradient problem by using residual or skip connection. With skip connection, gradients can propagate to shallow layers because they skip multiple layers. In this way, the gradients do not vanish. The same case with the improved version of ResNet. With residual connection and with batch normalization, ResNet achieved state-of-the-art performance on many vision tasks such as recognition, detection, and segmentation. ResNet addresses the issue of gradient explosion by using batch normalization or BN. Batch normalization is an effective technique to stabilize the gradient. The idea is very simple. For each layer, keep the batch mean 0 and the variance equal to 1 for all activations. Even with high value of learning rate, BN keeps the training stable. In summary, CNN is a parameter-efficient, parallelizable, translation equivariant, and scale invariant model. Before transformers, CNNs dominated most of vision tasks. In this slide, we show AlexNet. This is the deep neural net that won the ImageNet competition that ushered the deep learning era. Code demo is next. This is our code demo. In this demo, we will show how to build and train a CNN model, and we will use CFAR10 dataset. In this demo, we will build and train a 3-layer CNN model. We will show 2 implementations of this CNN model. The first one is through the use of the PyTorch built-in Conv2D. And the second one, which is a little bit more challenging, but is really educational in the sense that we will really understand the process of convolution, is we will do convolution on the tensor level. Now let's see the demo. The first one is we will import the necessary modules, just like in the previous demo, and then we will build the first CNN model that is based on Conv2D. So in here, you will see that there are 3 convolutional layers. And this Conv2D by default is using NN-Conv2D of PyTorch. So here, by default, we will use a kernel size of 3. So that's basically 3 by 3. And the filters starts with 32. But as you can see here, as the filter is doubled after every layer, we will see that the feature map size is half every after layer. And this is done through the use of max pooling. So one thing that's very important here is the number of filters output of each convolution should match the number of filters, the number of input features of the succeeding convolution. Now, there is, however, a little bit problem challenging here because the last layer is a linear layer represented by FC1. Here, we need this configuration of NN linear, which is 2048 by num clauses. Num clauses is basically the number of clauses in CFAR10, which is 10. However, 2048 is a bit challenging. Where did we get 2048? That's actually the number of feature points after the third convolution. Now, how do we compute that? Well, normally the technique that I use is I will first comment out the last linear layer, which is FC1, and then I will print the shape of this Y. In that shape, we will see that the shape is 2048, and that's the one that I will encode manually. Now, if you are going to train this model, we will use a lightning module, and the lightning module that we will use for this case is the same, almost the same as the lightning module that we use for CFAR10 using MLP. So basically everything the same, except that we will change the model. We will change the model to simple CNN. Now, here, however, we use different types of convolution. So for the meantime, we will focus on the built-in PyTorch convolution. Now, if you train this model, this is the lightning module. Basically, all the discussion MLP for the lightning module still applies here. We will train for 30 epochs using Atom Optimizer, cosine annealing for the learning rate scheduler. We will use GPU, one of the one GPU, after the 30 epochs, we will get an accuracy of about 73%. 73%. That's actually good, considering that our benchmark, which is ResNet 18, is about 78%. And our earlier simple MLP model is about 53% only. Furthermore, here, we will see that the number of trainable parameters is 113,000 only. That is really small compared, for example, to ResNet 18, which is about 11 million plus. So this is really very efficient model, even though this is just a 3-layer CNN model. So here, if you train this model, by the way, in this case, to speed up the training, we disable the 1B logger. If you want, you can enable the 1B logger. So after training, you will see it's about 73%. Now, the next thing that I want to emphasize here is if you can also do the same, you can also build the same model, but at the tensor level. That is the more challenging part. Now, if you go back here, it took me a while to figure out, of course, how to build this tensor level convolution. But one thing that will help you to figure out the convolution on the 2D level is to implement it on the image level first. So in this case, I implemented the convolution using a 3x3 filter on an image. This is the image, an image of a cat. So I filled my kernel by ones. So all ones, all elements are one. So in theory, if your convolution is correct, then the output convolution should be a grayscale, because basically convolution is a dot product. The dot product of the kernel, which is all ones, and the dot product of a 3x3 patch. So basically, the result of the dot product is 1 point, because recall dot product is element-wise multiplication, and then you sum up all the result of the multiplication. So that's equivalent to 1 point. So each patch, which is 3x3, convolved or dot product with the 3x3 kernel is converted to 1 point. So basically, our 224 by 224 image is about 74 by 74 patches. So the result is just 74 by 74 pixels. So you can easily imagine that this is not sufficient for us to represent our original image, which is about 224 by 224, into a grayscale. That is because imagine that the convolution process is just like sliding window. So at the topmost, you slide 1 pixel at a time. And from the topmost, you move down 1 pixel and you slide again 1 pixel at a time. So basically, we still lack 8 additional configurations because we skip by 3. So in here, that's the reason why we have 2 for loops. One inner loop, which is will loop 3 times, equivalent to kernel size, and another outer loop, which will loop also 3 times. The inner loop basically adjusts the edge. Originally, the edge is aligned with the image, and then next it will be adjusted by 1 pixel, and the last one is it will be adjusted by 2 pixels. The outer loop adjusts the edge at the topmost. Originally, no adjustment. In the second one, there will be adjustment by 1 pixel. In the third one, there will be adjustment by 2 pixels. So all in all, if you put together all the results of the convolution, this is how we put it together. This is how we reassemble all those outputs of dot products or convolution or multiplication of the feature with the kernel as shown here. then we will be able to recreate the original image in the form of grayscale. But take note, since that is dot product, the result is not necessarily normalized. So we still have to normalize it by dividing the output tensor by its maximum value. So if you do this, you can see this is the original image. This is now the resulting image. And from here, you can see that the max is not necessarily equal to 1. And the minimum is not necessarily equal to 0. So you can normalize this result of convolution by dividing it by the max of zig. So with this convolution process in mind, that's very important. That's the algorithm. Basically, that's the algorithm of convolution. You can recreate that algorithm using PyTorch Tensor. This is how we are going to replace Conv2D of PyTorch. Basically, we will create Tensor Conv2D, our own Conv2D. Here, the most important parts are the kernel and the bias. And both are parameters, meaning say they will accept gradients. In addition, we need to reset the parameters. So as you can see in the earlier discussion, MLP, without proper initialization, the MLP will not converge. The same case for convolution. It's not going to converge easily if you don't properly initialize the parameters. So the forward call is basically the same as the algorithm that we presented earlier. Now, the only difference in this case is there will be an additional axis. That axis corresponds to the batch size, because our processing during training for the CNN model is by batch. So everything the same, except that we operate at the PyTorch tensor level, and we can process this at the CUDA. So that's a lot faster than doing it on CPU. Now, if you're going to change the convolution from NN Conv2D, just replace it by Tensor Conv2D. Simply uncomment this and comment this one, and then retrain everything. You will discover that the number of parameters exactly the same. The accuracy is almost the same, 73% plus. But this version of convolution is slower by a factor of 2. That is understandable because we did not optimize the part. We can still do a lot of optimization here because, as you can see, we are doing 2 loops. So, but this process here can still be parallelized. So if you can parallelize this further, then you will gain additional speed. But this is already parallelized because for each iteration, when we do the dot product, we do the dot product for the entire number of patches of the feature map. The only problem is we have to do it 9 times, equivalent to the 9 requirements of the 3x3 kernel. But if you come to think of it, those 9 loops can be done in parallel. So that is where the additional speed up can originate from. So basically, that's our demo. I encourage you to do additional experiments, and the additional experiments that you can do here are listed here, like trying other kernel size, maybe increasing the depth of the model, and you may want to try other activation functions like JELU, for example, and you might try experimenting. What if you add skip connections? That's it. Thank you.